Hello, multiplication explorers. Maria Drushkova here, doing my favorite part of the course, looking at everybody's questions. Now, do you know what we did here? We really created a group of questions that can be a start of a beautiful, long exploration into tree fractals. You can use this to write a dissertation, or you can use it to play with toddlers to just explore online. So there is no way I can answer all this in a short video, but I'll try with some. And some of the questions are whys and hows. Can you explain what this has to do with math? I'm not seeing the link, what the drawing has to do with math. So this brings me to the question of what mathematics is. What is mathematics? When do we do math or make math? So one of my favorite answers is that mathematics is all about patterns. Well, then what is a pattern? And that brings me to my second favorite answer, that mathematics is seeing similarities in different things and differences in similar things. So towards that goal, I made a Google search for fractal branching in images. And this is a fun thing to do with kids, just search for some pictures, look at pictures together. So these are all different pictures, but we see the similarities. So what does it do for us? We see this big pattern of branching and branching again. And once we see the pattern, we can ask questions about the pattern. Do things branch differently? How many branches in each pattern? Where else this branches happens? So I'm going to scroll down for some applications or scavenger hunt. So this is a plant. I think deal. These are a couple of different trees. These are artistic or mathematical fractals, artificial ones. These are human lungs. And you can see the branching here. So some other nature, I don't know if these are rivers or plants. And do I care? Because I see the similarities in mathematical patterns. The heart, the lightning, lungs, plants. We see similar things in different objects. We see that similar pattern. And then we can ask for more similarities, such as which of these things branch in the same number or in the same way? How many levels of branchings do we have? And so on. So this is where mathematics comes from. This is where you start doing mathematics. You seek those patterns in different things. So there were some other questions I wanted to address, and I hope people will go through these questions and answer one another in comments. And let's see what else is there. There were several questions about random blips in the pattern. For example, trees are not always regular, fractals in nature, does it count? And the same question is about children. Well, children make mistakes sometimes. Does it count if the fractal is slightly messed up? So mathematically, you can introduce randomness into your fractals and explore that. The nature always makes little mistakes, of course. So there are all the trees are slightly irregular, and there are always these great arguments between kids who I call little engineers and little mathematicians, like in those jokes. So little engineers point out these imperfections, and little mathematicians say, well, I still see how the whole thing works. I still see the rule. So it's a good way to discuss things. And another question is about learning that I wanted to point out. My child recognizes and correctly predicts exponential growth, but only as long as there are pictures to support the story. Why? So this is a very interesting question, and you see it again and again. You see a kid doing brilliantly in one context and then not doing things at all in another context. The same is true for grown-ups in very dramatic ways. For example, in one study, pediatric nurses in a hospital made 0 mistakes on the ward. In a month of observation, they mixed all their drugs correctly and administered them to the patients. And then the same nurses got a mathematical test about the same kind of mathematics they use to mix the drugs, but expressed formally. And they made about 40% mistakes. So switching from one context to another, from one representation to another, is always problematic. How can we help our children to get to the high level of abstraction, to see the connections, to see the ocean in the drop of water? I think the good way is to explore these ideas in different contexts. So basically, someone else asked, what types of fractals are there? We look at 2 types in this course, tree fractals and substitution fractals. And you can look around, see some different types like Julia fractals. All fractals have parts similar to the whole. That's their general description. But with kids, when you see exponential growth in fractals, and then maybe in zoom and powers, and then maybe in measurements, and then maybe in algebra, and every time you ask yourself the same mathematical questions, what are similarities between these different things? And the kids can explain similarities in their own ways, but they will find some similarities, and eventually they build this overarching idea of exponential function, I guess, or exponent as an operation in different contexts. We have this rule of 3 that you need to see the idea in 3 or more different contexts before you can form a general understanding of it. So seeing pictures of one thing like fractals is not enough to support exponentials, but seeing different contexts and pictures in those contexts and then connecting, that's when you form an idea. These are all questions for today. I can't wait to see what tomorrow brings as far as questions go. See you on the forums.